And yet, despite the harsh conditions, despite the scarcity of food and the crushing pressure, life persists. The abyss is not empty. It's a desert, yes, but even deserts have oases. And in the deep ocean, those oases are among the most remarkable ecosystems on Earth. In 1977, a team of scientists descended to the Galapagos Rift in the submersible Alvin. They were studying the mid-ocean ridge, the volcanic mountain chain that runs through every ocean on Earth. What they discovered changed our understanding of life itself. As they explored the seafloor, they noticed temperature spikes in their instruments. Water that should have been near freezing suddenly registered at 12 degrees Celsius, then 17, then 22, and then they saw them. Chimneys. Tall structures rising from the seafloor, some as high as buildings, pouring dark fluid into the surrounding water. The fluid looked like smoke, billowing and spreading, and the scientists called these structures black smokers. The temperature inside the vents reached 400 degrees Celsius, hot enough to melt lead. Superheated water shot from the Earth's crust, loaded with minerals dissolved from rock. When this mineral-rich fluid hit the cold seawater, the minerals precipitated out, forming the chimney structures. Iron sulfides, copper, zinc, silver, gold, all raining down and building up over time. But the temperature and chemistry should have been lethal. The water was acidic, toxic, full of heavy metals and hydrogen sulfide. It was like a chemical soup, a poison cloud. And yet, surrounding the vents, the scientists saw life. Not just life, but an abundance of life unlike anything they had seen in the deep ocean. Giant tube worms, taller than adult humans, their red plumes waving in the current. Mussels and clams clustered in vast beds around the vents. Crabs swarming over the rocks. Shrimp and fish swimming through the mineral-rich water. The scientists realized they had discovered an entirely new type of ecosystem. An ecosystem that didn't rely on sunlight. An ecosystem built on chemosynthesis instead of photosynthesis. Chemosynthesis is similar to photosynthesis in that it produces organic compounds from inorganic ones, but instead of using sunlight as an energy source, it uses chemicals. Bacteria at hydrothermal vents harvest energy from hydrogen sulfide, a compound that's toxic to most life. They oxidize the sulfide, extracting energy from the chemical reaction, and use that energy to convert carbon dioxide into sugars and other organic molecules. These bacteria become the base of the food chain, the primary producers in a sunless world. The giant tube worms, called Riftia, have no mouth and no digestive system. They cannot eat. Instead, they house billions of chemosynthetic bacteria inside their bodies in a specialized organ called a trophosome. The worms provide the bacteria with hydrogen sulfide and carbon dioxide, absorbed from the vent water. The bacteria produce organic compounds that the worm absorbs and uses for energy. It's a perfect symbiosis. Neither organism can survive without the other. Riftia can grow to 6 feet long, and they grow fast. Unlike most deep-sea creatures that mature slowly over decades, tube worms reach full size in less than 2 years. The abundance of energy at the vents allows rapid growth. Food is not scarce here. Energy flows constantly from the Earth's crust. Vent mussels, Bathymodialis, also house chemosynthetic bacteria, but their bacteria live in their gills rather than in an internal organ. The mussels position themselves at the edge of vent flow, where toxic vent water mixes with oxygenated seawater. This mixing zone provides both the chemicals the bacteria need and the oxygen required for the oxidation reaction. The mussels are often the first colonizers of new vents, and they can survive for a short time even after the vent shuts down, living off stored energy. Vent crabs, pale white and eyeless, swarm over the rocks and mussels. They're predators and scavengers, feeding on the bacteria mats, on worms, on anything they can catch. They're the top predators in the vent ecosystem, and they're well adapted to the extreme conditions. Their blood contains special proteins that allow them to tolerate high temperatures and low oxygen levels. Hydrothermal vents are not stable. They can shut down suddenly when tectonic activity shifts, or when lava flows block the cracks feeding them. Most vents remain active for only a few years to a few decades. When a vent dies, the community dies with it. The bacteria die first, unable to survive without their chemical energy source. Then the tube worms starve. The mussels filter the water and find nothing. The crabs move on or perish. But somehow, when new vents open elsewhere on the seafloor, they're colonized within years by the same species. Scientists are still studying how vent animals disperse across the deep ocean, how larvae find new vents, how these isolated ecosystems remain connected. It's possible that stepping stone vents exist between major vent fields, allowing larvae to spread gradually. It's also possible that some larvae can survive for months in the water column, drifting with currents until they encounter the chemical signature of a vent. The bacteria themselves are extremophiles, organisms that thrive in conditions lethal to most life. Some vent bacteria grow at temperatures above 100 degrees Celsius, higher than the boiling point of water at sea level. One species, Methanopyrus candeleri, can divide and reproduce at 122 degrees Celsius, the highest temperature known to support life. These bacteria don't just tolerate heat, they require it. They die if the temperature drops too low. Other bacteria at vents specialize in different chemicals. Some oxidize methane instead of hydrogen sulfide. Some reduce iron or manganese. Each species has carved out its own niche in the vent ecosystem, exploiting a specific chemical reaction, and together they form the foundation that supports all the larger life around the vents. Hydrothermal vents are more common than scientists once thought. They've been discovered in every ocean, from the Arctic to the Southern Ocean, at depths ranging from a few hundred meters to more than 4,000 meters. The deepest known vent is in the Cayman Trough at nearly 5,000 meters. Each vent field has its own community of species, some shared with other vents, some unique. The vents are islands of abundance in the desert of the abyss, connected by dispersal but isolated by distance. And they're not the only chemosynthetic oases in the deep sea. There are cold seeps too, places where chemicals emerge not from volcanic heat, but from the slow seepage of hydrocarbons through the seafloor. Cold seeps were discovered in 1983, 6 years after hydrothermal vents. Scientists exploring the Florida escarpment in the Gulf of Mexico at a depth of 3,200 meters noticed something unusual. Gas bubbles rising from the seafloor, chemical-rich fluids seeping from cracks in the sediment, and surrounding these seeps, communities of animals similar to those at hydrothermal vents. Tube worms, mussels, clams, all clustered around the seepage, all thriving in water that should have been toxic. The seeps are called cold because the fluids emerging from the seafloor are the same temperature as the surrounding water, or only slightly warmer. There's no volcanic heat involved. Instead, the chemistry comes from decomposing organic matter buried in the seafloor sediments. When marine organisms die, they sink and accumulate on the ocean floor. Over time, they're buried by more sediment, and as they decompose deep beneath the surface, they produce methane and hydrogen sulfide. Tectonic activity or sediment compaction can squeeze these fluids upward, forcing them through cracks and fissures in the seafloor. The methane bubbles up, often forming plumes visible on sonar. The hydrogen sulfide dissolves in the water,